All right, I want to look at how we can model different basic two-dimensional scenarios using vectors and sort of a list of strategies to help us even if the problem might not be familiar. So obviously step one is to read the problem. And once we do that, we want to draw a force diagram. Okay. So in this, it says a boat's traveling across a river with a current flowing 3 meters per second east. So I'm going to draw a little river, and the current's flowing 3 meters per second east. So there's current, and it's 3 in this direction is the magnitude. The boat has a speed of 5 meters per second relative to the water and is aimed directly north. I'm going to do some liberties in interpreting this problem. I think the intention is that we are directly aimed north and that the boat is generating 5 meters per second of force, not that the total resultant is 5. Okay. So here we go. Make it a little bit bigger. Well, whatever. So step one, we draw a force diagram. We've got a boat. We've got these two vectors that are acting on the boat. They have magnitudes of 5 and 3, so I'm just jotting that down. Those aren't the vectors themselves. That's just sort of to help me out. We got the force of the current, so I'll call that vector C, and we've got the force of the boat. I'll call it vector B, but you can call it whatever you want. And the magnitudes are 3 and 5 respectively. I'm gonna move this for a second. Okay. Next, we need to define a coordinate system. So we can't do anything unless we have an actual coordinate system to work around. And check out my last video if you want to see a little bit more about defining those. But this is pretty straightforward. We've got a river, we've got east, and we've got north. So really, any good logical coordinate system here is going to look like this, right? Why wouldn't we just draw our coordinate system aligned in this manner? We'll call this X, we'll call this Y. And then I like to situate my vectors right at the origin. It's the best place for them to be. So we put our vector here and we put our vector here. And let's just go over this again. Vector C and vector B. So we define our coordinate system, we kind of place our vectors in a way that makes sense, described by the coordinate system. Now this is a ridiculously easy system because east is the positive x direction. So the vector C is completely in the positive x direction. So it's 3, 0. And the vector B is completely in the positive y direction. So it is just 0, 5. Okay. They won't all be that easy to get in component form, but this works out very nicely. Step 3, we have to decide if this is a problem in which a object is moving or not moving. Okay. So we have to decide movement versus stationary or no movement. And a fancy word for stationary is static equilibrium. And it's possible that it's moving in one direction and not the other. In the case that it's moving, well, then vectors are very useful because to describe the net movement, we just add the vectors. In the case that we are stationary, or in static equilibrium, that means that the certain components must balance and cancel. And if they must balance, this means they sum to 0. Okay. So that's really the only two things we have to think about. Are we adding things to describe net movement? Are we adding things and making sure they equal 0 to describe stationary objects? All right, find the boat's resultant velocity, magnitude, and direction. So that's simple. The boat's net velocity, we just add the two vectors. So I'm going to put C up here now. Okay, add vectors, you just put them tip to tail. So the resultant vector velocity would look like this. We'll just call that V for the velocity vector. Super, super easy to add these two vectors because we already know their components. It's just going to be 3, 5. So the velocity vector of this boat, the net result is going to look like this. Velocity vector V has components 3, 5. Its magnitude is the square root of 34. And its direction is tan inverse of 5/3. Okay, and we can say I mean, we could evaluate that, but I'm not going to. How long does it take the boat to cross a river that's 100 meters wide? Well, if the river is 100 meters wide, and that is purely in the y direction. So we are completely unconcerned with the x. We want to know how long does it take to cross the y? Well, the part of the velocity that's being applied to the y is exclusively this, right? This is the only part of the boat's velocity that is in the y direction. So we have 5 meters per second in the y direction, and we divide 100 meters into 5 meters per second, and we get that it takes 20 seconds. Pretty easy. At what angle should the boat aim to travel straight across the river? Now this is where we think, okay, travel straight across the river. As it stands with the current and the direction the boat's aiming, our net effect is going to go down the river like this, okay? What we want is to actually travel down the river in this path. And because the current is going this way, we actually have to aim the boat somewhere this way to offset the current and make the actual resultant path equal to this path here. We want to go straight across. And here's the deal. This is now a stationary or a static equilibrium problem, because what we're basically saying is we need to aim our boat B, in some direction. Here's B. We need to aim it in some direction such that it is able to cancel the effect of the water. And the water is going 3 in this horizontal. The water is just the water. Canceling this 0, well, we don't even need to cancel the 0 because we're actually trying to cross and go vertically. We need to cancel this 3. So that means that, and I'm going to redraw a little new coordinate system here, x and y. That means that wherever we aim B, the horizontal component of B has to cancel out the horizontal component of the river. And so here, this needs to equal -3. It really, right, the horizontal part needs to equal -3i. Okay, well, how do we do that? Well, we know the magnitude of B. The boat has a speed, its power is 5 meters per second. So because it was just aimed purely north, straight across the river, we could say it's 0,5. But what we need to account for is that that's just the magnitude. And so if we just aim it this way, magnitude of B equals 5, well then this horizontal component is simply 5 cosine whatever this angle is, right? 5 cosine some angle theta. And it's that many i's. And that needs to counteract this 3. And so we can say that 5 cos theta has to equal 3. Actually, because it's counteracting it, it has to equal -3. So we're going to just put a -3 here. This means that cosine of theta is equal to -3/5. Okay, we're in a quadrant 2 angle, so cosine inverse is just fine. So theta is equal to cos inverse of -3/5. I'm just going to put that into a calculator. Arc cos, let's do it on Desmos. Just to give you a sense of what the angle actually is, arc cos -3/5, 2.21 radians. Let's get that to degrees. Okay, so it's actually about 126.87 degrees. So if I want my boat, if I want the path of my boat in real life to be like this, straight across the river, I actually need to aim my boat this way and drive like that, because what's going to happen is some of my velocity is going this way, the river's pushing me this way, those will balance out and I'll be moving across the river straight. So I'm essentially offsetting the effect of the current that's pushing this way by aiming the boat that way. Now, it would take you longer to cross the river because it took us 20 seconds if we put all of our velocity in this direction, that 5, and we just let the river carry us down. We land somewhere down the river right here. But if we are okay with that, then we can just put our boat straight ahead and cross the river as fast as possible. We just land right here. But if we instead want to cross the river straight across and we aim our boat this way, well, perhaps we'd like to know how much of our velocity is actually going in the direction across the river. And so we look at the vertical component in the positive y or the positive j direction. And that is simply equal to 5 sine of theta j. And now we know what theta is. So we can substitute that in, take 5 times sine of that, 5 sine of that, and we get 4, which should be a little unsurprising. So we have an actual net effect of 4 meters per second this way. So our vector b to go in the proper direction would be -3 in the I direction and 4 in the j direction, okay? Which is the same thing as 5 cosine of 126.87 and 4 sine of 126.87. Okay, so you should plug that in a calculator and verify that, but that is certainly true. Sorry, not 4, 5. Both of them have 5 times it, okay? And given that we're trying to oppose a force of 3, and this has to be a force of 3, this is a hypotenuse of 5, surely this should be 4. So now if we want to cross 100 meters, and we have 4 meters per second in the correct direction, 100 divided by 4 means it's going to take us 25 seconds. So it'll take us 5 seconds longer to actually cross this river, but we'll go straight across and perhaps land at our target location rather than some odd number of meters down the river. In this case, it would have been 60. You can do that math, but whatever. Okay. But our process is essentially this. Draw a force diagram, define a coordinate system, decide what's moving. You can just add those things, decide what's stationary, sum those things to be 0, then put it all together and solve. Okay, so that's a boat current problem, but this really works for basically whatever. Let's see, pulling an object with 2 ropes. It's kind of easy. Boat in a current, plane in the wind, ramps with friction. All right, let's look at a ramp with friction problem. The friction's a little, I don't know, a little more to think about. It pushes the physics more than the other stuff, but still, this is how we can approach these kind of problems without being too concerned. Okay. So a box weighing 25 kilograms is resting on a ramp incline. Okay, so we got to draw a diagram, step 1. Okay, 25 kgs, here's our box. Well, whatever, circular box. Great. And it's a 40-degree angle to the horizontal. This is 90 degrees. Gravity pulls straight down towards the earth. And so the force of gravity here is going straight down. It has a magnitude of 25. Step 2, right? We draw our diagram as much as we can. We also know that our interesting facts are how much of this is going down the ramp, and we might also need how much is pushing into the ramp for the normal force. So those are the 2 other quantities we're going to need, the parallel force and the perpendicular force. So we got to define our coordinate system. Well, here's the deal. Our most interested or most useful pieces of information are here and here, so it makes all the sense in the world to draw our coordinate system so that those are our axes. You could draw it anywhere you want, right? I could draw this and this, and I would be very wise to do so, but I could also draw a coordinate system like this. I can work with that. Why would you? I don't know. You could maybe make an argument for drawing the coordinate system with gravity being down. Yeah, maybe if there's enough going on, but since this problem is pretty straightforward, we're just going to actually draw our coordinate system like such. Okay, so we're going to put x here, we're going to put y here. Great. Now the vector that is the force down the ramp can be drawn directly on this x-axis. We can call that the force parallel. Yeah, I'll just write it, force parallel, some vector. And then we have the force into the ramp, or the force perpendicular. So we can say the F perp. Actually, I'll do F perp for F perp, and F parallel for F parallel. Okay. We reason with this problem. Hopefully you've seen these enough that you can say, oh, okay, this is also must be a 50-degree angle. Therefore, the parallel force, F parallel, it must be equal to the magnitude of FG times the cosine of the angle 50, or I'm going to call it negative 50. So 25 cosine negative 50, and 0 in any other direction. And the force perpendicular is equal to 0 in the direction down the ramp. It's completely into the ramp, and that is equal to 0 comma 25 sine negative 50 degrees. And let's throw FG in there. Yeah, why not? Force of gravity is the combination of these two. It's the parallel and the perpendicular. It's this in our coordinate system, 25 sine. So it is the sum of those two forces. So what have we done? We've drawn a diagram, defined a coordinate system. We haven't really looked at movement versus stationary yet. We're still setting up our basics. But because we've done problems like this before, we know these are the vectors we're going to need. Okay. We actually don't know if this box is moving or not. In these friction problems, we're not actually sure. So we drew our diagram. We found the components parallel and perpendicular. Find the maximum force that friction can exert. So now we're just using a formula. The force of friction max, the max force that friction can exert, which is a magnitude, or I'm putting that for clarity, is equal to the coefficient of friction, in this case 0.25, and that is being multiplied by the magnitude of the normal force, which is F perp. How hard we push into the ramp tells us how much that coefficient of friction sort of gets activated. And so this is the magnitude because this is 0, has no effect on the magnitude. So we multiply it by 25 sine negative 50. Okay, so the max that friction can actually exert is just a value. This is fine not to have. We can put this into a calculator, so I'm going to say 0.25 times the magnitude of 25 sine negative 50. And so I'm getting that the maximum amount of force that friction can oppose is 4 pounds. Okay, so friction can oppose 4.79 pounds of force, and it can resist movement that much. Find the net force down the ramp. Now, net force is a pretty good indication that we're just adding forces. So that means we are taking this parallel force that's acting down the ramp, and then the friction force, which resists motion. So if it's going to resist that force, because that's all that's happening. And so we can say that we can take the F parallel and add it to the force of friction. One note is this is a magnitude. I'll put it back in magnitude. The actual force of friction, FF max, or force of friction max, in this case, is going to be a vector. It's not 100% this, but it's more or less this. It's only acting in the x direction. It's acting in the negative x direction. This is the most it could do. It's not saying it will do that much, but it's the most it can do. So FF max plus F parallel is equal to the net force down the ramp. Okay. Add these together, pretty easy. Negative 4.79 in the I component, 0 in the J component for F parallel. For F friction is this. F parallel we said was 25 cosine negative 50, comma 0. So now we just sum them up. And easy enough, let's just do a calculator. Add that to 25 cosine negative 50. So our net force is 11.28 pounds of force down the ramp. So the net force down the ramp this way is 11.28 pounds down the ramp. That's with gravity pulling and friction opposing. If you want to see just what gravity would do without friction, gravity is doing 16.07-ish, and friction is doing opposite that, negative 4.79. And so the net result is that. Okay. Finally, find the force required to push the box up the ramp at a constant speed. Constant speed's not too detailed. It's just saying there's no acceleration. We can mostly ignore that. So required to push the box up the ramp. So we need to overcome the parallel force down the ramp. And sneakily, we also need to overcome force of friction, because once we push hard enough, the box is not going to be, the gravity is going to be counteracted by us pushing up the ramp. And so then friction is going to oppose us, and suddenly friction is going to start going this way, right? Friction's like, hey, I don't want to move. If you're about to move this thing, if you're taking care of the weight, suddenly I'm going to push this way and then oppose us. So how much force are we going to need? It's simply 16.07 plus 4.79. So let's just do that real quick. So it would actually take 20.86 pounds of force to push this box up the ramp. Even though the weight of the box is only this, friction is going to oppose us this much. So friction is going to oppose the box sliding down the ramp if it's only gravity, but if we're trying to help, it's going to push against us. And so there we go. So this is a little bit more nuanced because we have to know a little bit about the physics behind this. But our process is kind of similar in that we draw a force diagram, define a coordinate system, think about, are we moving? Do we add things and just see what the movement is? Is it stationary? Do we see what adds to 0? And in this case, it really was more of a movement problem, right? We want to know, is the box moving? And the answer to that question really lies in summing these things up and seeing, is it more than 0? So that's kind of that. We'll do one more here. Okay, let's look at D here, because I think this will maybe be a good situation. I find these a little bit easier, but still, the principles apply. Two people are pulling an object with ropes at angles of 35 degrees and negative 50 from the horizontal. Okay, regardless, here's the object. We're just going to say this person's pulling this way, this person's pulling this way, and here's a horizontal. So our vectors exist. The magnitude of this vector is 90. The magnitude of this vector is 120. This is 35 degrees. This is negative 50 degrees. Okay. So step one is sort of label vectors and forces and whatever. We'll call this person 1, F1, person 2, F2. And I'm purposely putting F2 not right next to the 90 or the 120 because those are just the magnitudes. Like I'm writing that so I know, but the vector itself is not its magnitude. All right, now I need to define my coordinate system. This use of the word horizontal really makes it logical that this is our positive x direction and this is our positive y direction. And this is the extension of our coordinate system. Try to make that a little less shaky. Okay, great. Find the resultant force. Okay, resultant force, net force, blah, blah, blah. That's just saying add the two forces. So we're adding force 1, we're adding force 2. Now, the best way to add these forces is to break them into their components. So this is equal to F1, magnitude of F1 sine 35, 90 sine 35. This is 90 cosine 35. So F1 in component form is 90 cos 35, 90 sine 35. Likewise, F2 we can pretty easily say is 120 cos negative 50 and 120 sine negative 50. So we have F2. Great. All right. And so if we want the resultant force, what do? We just add them up. We add these two vectors and we get some resultant force. So we're just going to add their components. I'll type that in a calculator. 90 cos 35 plus 120 cos negative 50. And the result in the, I'm going to call F net, is equal to 150.86-ish in the x direction. Let me sum the y directions. 90 sine 35, 120 sine negative 50. So we get negative 40.3-ish. Okay, so that's F net. Easy enough. Determine the component of the resultant force that moves the object directly forward. Okay, it's a way of asking about the horizontal part. So that's simply 150.86 pounds is moving in this direction. So that's the force moving forward. Okay, so we've just done some summing problems, right? What did we say? We said movement. This thing's moving, we are adding, and just sort of seeing the results. So our net vector, if we added these two things, right, we can put them tip to tail as if we wanted to add them. Our net vector looks like this. Diagram's getting a little clouded, but that is F net. Okay, I'm going to get rid of some stuff. Clear this up a little bit if I can. Okay. Now, instead of that, we want to say, how could person 2 modify their angle so that the object has no vertical movement? No vertical movement. Now we are in a no movement problem, right? We have movement problems. We have stationary, no movement, static equilibrium problems. That means the components must balance. They must sum to 0. We've got a no movement problem. We want no vertical movement. So their vertical components, this and this, must sum to 0. We are only allowed to modify person 2, so only this angle can be modified. Person 2's still going to pull with 120, but we're going to change that angle so that they completely balance. Okay, so it's a equal 0 situation, which I'll write. So 90 sine 135, or sorry, 90 sine 35 plus 120 sine. At the moment, we're going to have a theta because we're saying we're changing this angle to some theta, right? We don't know where, but somewhere is going to be a theta such that these components actually balance. And all that is going to equal 0. Simple. Can we solve this? We sure can. So 120 sine of theta is going to equal negative 90 sine 35. Sine of theta going to equal negative 90 sine 35 over 120. Now I can simplify that. 9/12 is 3/4. So we get theta is equal to sine inverse negative 3/4 sine 35. Pretty interesting. So we're going to get a theta value here. So let me put that in. Arc sine of, I'm going to do a decimal negative 0.75 sine 35. And what do we get? A negative angle. We check the reasonableness of this. Negative 25.48 degrees. Yeah, this kind of checks out. We were at negative 50. We're bringing it back somewhat, negative whatever. Now we're at negative 25. And that has shrunk our horizontal component enough that it should balance this. Okay, we can even check that fact. Does 90 sine 35 balance versus 120 sine of negative 25.48? Probably. Let's put it all together just to check. 90 sine 35. We get 51.62. And if we do 120 sine of negative 25.48, guess what? We get 51, well, negative 51.62. These two forces, are there forces this way and this way? Add them together, they completely balance each other out and result in pure, clean horizontal motion with no vertical component, because these still have horizontal components. Okay, so look at how I'm attacking these problems, right? Same problem-solving process. Draw a force diagram. Define a coordinate system. Are we moving? Are we stationary? Do we just add things up and just see what the result is? Do we think about components that must balance and sum to zero? Okay, that's all there is to this. There may be a system of equations you have to do in a tension diagram. You might have to know a little bit about physics and friction. But once you have those really couple of pieces of information that you know, the problem-solving process really just revolves around this. Okay. Okay. Cool. Hope you enjoyed this. Thank you.